All right, welcome everybody to our SUSECon session on zero-touch provisioning at the edge with Cluster API and Metal3. My name is Tim Jönich. I'm the product manager for our Telco Edge solution, and I have with me Jason Dobies, who is our lead engineer from the Edge BU's engineering team. And we will take you through this presentation, and we will, of course, have a demo in the second half of the talk as well. So what we're going to take you through today is, first we will briefly touch upon what Edge actually is, just to set the context. And then we will basically explain how that leads over to the problem Metal3 and Cluster API are solving, and why that is a relevant problem to solve in the context of Edge. And then we will basically show you how that particular part of the puzzle works, provisioning Kubernetes clusters onto bare metal servers, through a declarative API. So there's a lot of talking about Edge, and there are a lot of definitions out there. I think it's fair to say that the industry as a whole hasn't really converged on one unique definition of what Edge actually is. And that is also visible in this questionnaire here, where people have been asked, what is edge computing to you actually? If you look at the different answers and how often they have been given, you can see that there is, first of all, if you look across these answers, you can see a couple of patterns, right? I think one pattern that is in all of these answers basically is that it is a different location than the typical data center location, right? So what we're talking about is compute infrastructure, which is located somewhere, and that somewhere is, the only way that somewhere is defined is that it is not the data center. And that is actually, as we believe, the gist of what Edge really is about. It is about trying to use the same technologies that have brought us so many efficiency gains and so much additional and better control over our infrastructure that have been originally invented in the data center, also outside the data center. So the definition that I personally like best, because it focuses on what Edge is really about technically, is it's about seeking the benefits of data center technology, and particularly the way data centers are managed in locations that are not data center locations. And what I mean with these technologies is anything that has to do with virtualization, containers, Kubernetes, infrastructure automation, and as a result of that, all the improvements in terms of agility, total cost of ownership, and the ability to manage infrastructure remotely without having to do the traditional walk to the rack, plug a cable in, go to the serial console and watch what the server is doing with a keyboard and a mouse and a monitor attached. So if we let that sink in for a second, if we can agree for the purpose of this presentation that Edge is about using what has been invented in the data center outside the data center, we could basically stop the presentation here if it wasn't for the fact that data center stacks are actually not really built for the edge. Data center stacks are obviously built with, and what I mean with data center stack, by the way, is mostly everything that has to do with managing the infrastructure in a data center. So it has a lot to do with, again, management automation, observing a large number of clusters. And as we all know, there is a fairly large range of tools that have been invented for that particular purpose over, let's say, the last 2 or 3 decades. But if you take just those technology stacks that are used to manage data centers today, and you try and apply them to edge scenarios, you inevitably realize quite quickly that there are a couple of distinct differences between edge locations and data centers that require an additional iteration in terms of technological advance for those stacks. And I'm just calling out 4 examples here. There are probably more if we want to be complete, but those 4 are actually, I think, what's most important for the presentation here today. The one very important difference between edge and data center, obviously, is that in edge locations, you always have limitations in terms of physical hardware availability or the capacity that you can realize based on the available physical hardware. So the management stack that is used for an edge installation is like the footprint that management stack has gains significantly more mindshare compared to a data center scenario, because the system overhead of management stacks in data centers is just so negligible compared to the overall available capacity in the typical data center, that people basically don't have to worry about it. But in an edge location where you may just have 3, 4, maybe 10 or 20 servers, it obviously matters if 2 of those servers are completely eaten by your management stack and you can't actually run any productive workloads on them. Edge locations are oftentimes also characterized by insecure physical environments. Obviously, data centers are relatively easy to secure in terms of physical access, but edge locations aren't. They can be very, very uncontrolled. So anything that has to do with zero trust and secure device onboarding, making sure that the device you're onboarding into your infrastructure is actually the right device and it hasn't been tampered with on its way there, is super important. And it's a new problem field that comes with edge that hasn't to that extent existed in the data center before. Another area is that oftentimes in edge infrastructure, you don't have qualified personnel on site, which basically means everything has to be able, you have to be able to do everything remote. And that is specifically what we're talking about today here. You have to be able to bring up your infrastructure basically from unprovisioned bare metal completely remotely. The only you have to reduce the manual interaction with the physical hardware on site to the bare minimum of basically racking and cabling and powering it and like making sure that it powers up initially, and then everything else has to happen remotely. And of course, not only the initial provisioning, but also the entire life cycle after that, like anything that is typically referred to as day 2 operations. And then the last thing I want to touch upon is if we're talking about edge scenarios, we're talking about thousands, 10,000s, and maybe in some cases hundreds of thousands of sites. So the scale of edge infrastructure, even though each edge site, of course, is typically relatively small, but the scale of the entire infrastructure you may have to manage can be significantly larger than what a typical data center contains, even the big ones from Amazon and Google. So you need even more automation and even stronger templating mechanisms to make that manageable with reasonable human effort. And that is actually my transition to getting a little bit closer to what we're talking about today. As a result of all those things, you end up with a challenge that has to do with ensuring compliance and preventing drift. Because if you have all those thousands, 10,000s or 100,000s of your edge clusters, which tend to be identical copies of one or a small number of templates, you have to make sure that your actual infrastructure is always in line with your definition of how the infrastructure should be looking like. Even if you make a small change for maybe troubleshooting purposes, or just someone goes into one particular cluster and tries to modify something, you have to make sure that those changes are either not possible at all, or that they at least get detected and that there is an easy way to take them back. So how do we manage edge at scale? As I said before, the answer basically is even more automation. And this splits up into two distinct areas that we're presenting here today. One is you have to use a declarative API to deploy and manage the entire stack. And I say deploy and manage because this is basically the entire life cycle from day 0 all the way down to deprecating and having a hardware refresh and rolling out your next generation of hardware. And then something that has a lot of traction in the industry, is particularly in the context of running Kubernetes and running Kubernetes at the edge, is the principle of GitOps, which in a nutshell means storing your infrastructure definition in a revision control system like Git, and then having a so-called GitOps engine, which continuously syncs the actual state of your infrastructure with the wanted state that is stored in Git, which basically means that in order to effect change onto your infrastructure, you have to submit that change into your Git repository, and then the GitOps engine picks it up from there and rolls it out into the actual infrastructure. An often overlooked consequence of that concept is that even though you may be able to access the resource definition in your management infrastructure directly and manually, and you could theoretically change it, your GitOps engine will actually see that the deployed state of the resource is different from the one that it finds in the Git repository, and it will either prevent you from making that change or it will immediately take it back. And that's actually the wanted behavior for, let's say, the default operation. Of course, there are special scenarios in terms of troubleshooting or experimentation where you may want to deviate from that pattern, but the normal pattern is the single source of truth is Git. Any other change that doesn't come from there should be prevented or reverted immediately. The way we implement this in our Edge solution, and I'm showing this here at the example of the telco stack that I'm responsible for as a product manager, but we will find that pattern in the other vertical stacks that we provide as well, is that we have a central management stack based on Rancher as the underpinnings, plus a couple of enhancements with in the form of a GitOps engine, in the form of integration of Cluster API and operating system and bare metal management functionality that we will show you in a second. And that is the management stack that can be used to deploy the managed application runtime stack, one or more instances of that stack in a given edge location, then managing a large number of edge locations of that kind. So speaking of Cluster API, and this is now actually my last slide before I hand over to Jason. Cluster API is a project under a special interest group in the CNCF, which is called the Special Interest Group Cluster Lifecycle. And the main deliverable, besides actually delivering kubeadm as like the upstream reference implementation for a Kubernetes installer, is that they are developing an API for declarative specification of Kubernetes clusters, because they realized that that was basically a missing piece in the ecosystem. What is nice about this API that is done by the CNCF is that it is a vendor-neutral interface that you can use to express your infrastructure requirements, your policies, everything that has to do with setting up your clusters correctly, because that is where your engineering team will spend their cycles. If everything else is well automated and you have a management stack that allows you to focus your effort on making sure that you are mindful about how your infrastructure is composed and configured, this is where basically the brain power of your engineering team will be. Defining the templates, making sure that the policies are correctly implemented and all that. So it is very important that this investment that your engineering team will make is expressed in a language that you can take along with you as you move maybe from one vendor to another, or as your infrastructure management solution evolves. Cluster API is designed around a concept that is called providers, which is actually one relatively well-known design pattern in the industry. And there are specifically two types of providers, or strictly speaking three, but the latter two are kind of related to each other. There is the infrastructure provider, which essentially turns machines from an underlying infrastructure. It provides those machines to you. Like if you're, for example, running in public cloud, it will create the cloud instances for you and then hand them over to the Bootstrap provider so that it can then turn an infrastructure machine into a Kubernetes node that it can basically add it to your cluster, or bootstrap a cluster onto a node if the cluster doesn't exist yet. And then the control plane provider is kind of the day two brother of the Bootstrap provider, because it represents the Kubernetes cluster control plane basically in day one and day two scenarios after the initial bootstrap. So why is that important? It's because infrastructure providers for bare metal, like the one we're talking about here today, are a little bit special. Because if you think about the concept of an infrastructure provider for a public cloud for all intents and purposes has infinitely many machines and resources. You rarely end up the Amazon API telling you, sorry, I don't have any machines available anymore. So there are always as many machines as you like. If you're managing your own bare metal infrastructure, you obviously have to create an inventory of available infrastructure machines first. And then the infrastructure provider's role is a little bit different, because it basically just matches what is the right machine to pick from the existing inventory for the purpose that you are that you want. Like either you can create a cluster that doesn't have a particular opinion about which machine it should run on, then the infrastructure provider will just pick one randomly from the inventory. But of course, there are also scenarios where you have an opinion that you express in your cluster definition about which machines should be used for a given cluster. And in that case, it's the role of the infrastructure provider to pick those machines, the right machines from an inventory. For example, the ones that have certain accelerators built in, that are in a certain location, or that have the right processor architecture. And with that, over to you, Jay. Let's have a look at the demo.
Awesome. Thanks, Tim. Quick introduction again. Like Tim said, my name is Jason Dobies. I'm the lead engineer for the Edge engineering team. I want to walk you through the demo today. Want to give you kind of a context setting to start with. So what we're going to be looking at is primarily a terminal-based interface. We jump to an ILO interface real quick to show some fun with bare metal booting, but you're going to be looking at a terminal. I am connected to an RKE2 cluster that has all of the pieces Tim described and more installed on it. So metal cubed, the CAPI APIs, and so on and so forth. Everything I need from a management cluster to then have it go reach out to two more hardware nodes in our lab and say, hey, I want you to provision this machine and make this my control plane for my workload cluster. And I want you to provision this separate machine and make this a worker machine for my workload cluster. We have 3 machines in play, 2 of which we were provisioning. Real quick, I'm going to mention I am a lazy developer, so I have aliased the kubectl command to K. So when you see it in my terminal, don't get too surprised. It's not any kind of fancy command. It is just base kubectl. Everything we're going to be doing is using base Kubernetes resources. I pull them up from time to time, but realistically, no one wants to look at a ton of YAML on screen. So there'll be other ways of kind of giving you that example outside of the talk. But for now, just come with us for the high-level pieces. So there's going to be 3 steps. It's pre-recorded across 3 different videos, largely because of time. I'm very good at speaking, but I can't sit there and vamp for 20 minutes while we provision a cluster and get everything set up. So we're going to see some time jumps in there, and that'll be pretty obvious when we're actually doing those jumps. So first step, we're going to inventory the bare metal machines. This is going to be us telling Kubernetes, hey, here's how you access the BMC on these machines. And then on top of that, it's going to go and boot those machines, do some inspection on them, and then come back and populate the resource and say, hey, this is what I discovered from a hardware perspective. That will define the workload cluster itself. So a lot of the things that Tim just introduced in CAPI or the Cluster API, we're going to see come back here with our cluster definition and saying that we want RK2 and so forth. And then the last piece is the glue that puts them together. This is where we tell Metal Cubed, hey, these bare metal hosts, I want you to use them to create a Metal Cubed cluster, and using the cluster definition from step 2, this is how we're going to provision it. Next slide, please. Next slide, please. I haven't chosen that one already. Again, what are our goals here? We are creating the management cluster representation. So Kubernetes resources, I feel like I'm harping on this a lot, and Tim covered it a bit, but these are all Kube native APIs. So everything you're used to working with in terms of pods and deployments and all of your other custom resources, it's the same exact interface that you're going to be using here. So we'll create those in cluster and management cluster resources. And then once we create them in the system, the metal cubed pieces will kick in and actually start the machines and populate those resources with some more information. Next slide. So real quick idea of the resource structure. So again, we're using Kube resources. There are a lot of them in play, and I very rarely pull up the actual YAML for them because it's very difficult to parse through in a 20-minute presentation. The bigger thing I want to highlight here is the kind of relationships and the resources we're going to be creating. And this first step is pretty simple. We have a secret for the BMC credentials. That is your built-in Kubernetes secret used for storing any kind of data you don't want just sitting out in plain text. And then our bare metal host in particular is going to point out, here's where the machine is itself. Next slide. You get an idea of what's about to happen because sitting in a command line, you get a feel for it. It's such a cool demo, and sitting in a command line, you don't fully get it if you don't understand like the pieces going on here. So Bottom left, we create this bare metal host, and that's the specification that goes into Kubernetes as a resource. The bare metal operator picks up that resource and says, hey, I have some work to do. It uses the OpenStack project Ironic under the covers. If that term is at all new to you, OpenStack is made up of a variety of sub-projects. Ironic is their bare metal provisioning piece, which has taken on a life of its own outside of OpenStack. We were able to, or I should say the Metal Cubed community was able to leverage Ironic to do all the heavy lifting of booting the machines and inspecting them and so forth. What it does is runs something called the IPA, or the Ironic Python agent, over on the bare metal machine, does the inspection necessary, which feeds back the data and tells Kubernetes, hey, we are ready to provision this machine. We can do something with it. Let's go. One more slide, please. I told you I'm not going to show you a ton of YAML. Believe me, there is a lot more here, but I wanted to at least pull this up. If you're still new to Kubernetes, there's largely two sections of every resource. The spec, which is me as the user defining this is what the resource is, and that's where it contains the secret and the BMC address and so on. And the status. And this is Kubernetes' way of capturing the state of this resource and bringing it back to the user. And I pointed out here because this is where we're going to see the results of that IPA, or that agent running on the bare metal machine. All of the inventoried hardware is going to come back and be stored in this status field. I have a note up there. It is truncated. There is quite a bit more data in here, but you can get an idea of the types of things that you're going to see in that information. Again, we're not going to go any deeper than this, but I wanted you to know that when the bare metal hosts boot up, they are reporting this information back into Kubernetes, and through the normal kube API, you're able to actually see these resources. So Tim, if you could do me a favor and bring up the BMH recording. So again, we're going to see some terminals here. On the left is where I do all of the work. I quickly bring up the YAML and so forth. We're going to see a tail on here. That top right tail, when you restart this, is going to be everything in the Kubernetes namespace for, could you pause, please? Everything in the Kubernetes namespace for Metal Cubed. I use something called kubetail, which is actually a really cool tool that will tail a whole bunch of pods in a single namespace. Just keep in mind it color codes them. So when you see red, that's not error. That is just kubetail's side effect. Having worked with this demo for days, every time I saw red, it kind of made me panic. But no, this is not a bunch of errors floating across the screen. It's just one particular output, the way they do the tail. Tim, can you rewind for a minute to go to the beginning, please? And the whole reason I'm having them go back here is I quickly jumped over in the video to show the ILO interface. And this is kind of the magic trick involved in all of this. When we get back to that point, you'll see that the bare metal machine we're working with is currently powered off to start. And that's very much an expected model. Excuse me one second. Okay, so if you hit play from here.
Hang on, I'm just trying to find it. Here we are.
Cool. So the two servers we're going to be working with, you can look at the top left under virtual power button. Hopefully it's easy enough to read. If not, just realize that little yellow button thing says off next to it. We're going to see that turn green during the demo as Ironic powers it up. So keep playing. So the first thing we're going to do is create the bare metal host and the secret. And on the left side, you're going to see me cat those files very quickly just to point out what's going on in them. The bottom right is simply a watch on the bare metal host resource. So I want to see it get created inside of Kubernetes. And then once I do, you can see I get a little space on the logs there. The logs are going to go nuts after I create those resources. And that is all of the Ironic pieces kicking in. That is all of the resolution for the resource. You can see in the bottom right our Kubernetes resource. So the actual bare metal host resource is coming back as the registering state. You can take a look on the left here. At the very bottom, the current event message has registering new host. Might be a little hard to see with the way the recording is going on, but thank you. That events tab or that events output is going to let us know everything that's going to be happening during the course of the provisioning process, or I should say the discovery process in this case. Here, I got a tad bit impatient and hit refresh before the page had a chance to do it itself. When it comes back, you're going to see the server has been booted. It's going to be booted into that ironic Python agent image that I spoke about earlier, and that's going to be doing the discovery for us. So you can see, there we go. The green button is the switch to on, automatically booted for us by ironic. And in a second, the demo is going to swap back. Actually, it's going to swap over to the terminal here so you can just see it booting. So again, it feels a bit like a magic trick of like no hands and suddenly there's a machine booting. So at this point, it's running through all of the inspection. It's copying down the IPA image from our media server. It's doing the inspection. Time passes, and now when we come back, you can see in the bottom right, the bare metal host state has flipped to available. So all of the inspection has taken place. If we look on the left side, a little hard to see, but that field at the top, 2/3 of that screen is now significantly longer. That is all the status information we saw on the slide. And the events in the bottom left tell us that the hardware inspection is complete. All right, will you jump back to the slides for me? So at this point, we have bare metal machines inventoried inside of our management cluster. We can see information on them. We can see the data that was scraped during the inspection process. Go to the next slide, please. And this can just sit idle for a bit. This can hang out until we're ready to actually provision clusters. I actually just had a conversation with someone asking what the flow looks like and do you create them all at once? You absolutely can. We've seen demos run that way. For simplicity, because there's a lot of moving parts, I broke it into 3 distinct steps, figuring you're going to get the machines in first and get them all inventoried and ready to go. Next slide. So our next steps are to define the actual workload cluster and what it's going to look like. Which Kubernetes distribution, which is obviously going to be RKE2 for a variety of reasons. How the cluster itself is going to be configured. And if I've ever made a loaded bullet on a slide before, simply cluster behavior configuration as a one line does not fully encapsulate what it takes to configure a cluster, as you can imagine. But you got to realize that's all of the flexibility you would want in your workload cluster. It feels very hand wavy to be like, yeah, just some config. It's cooler than that, trust me. And then some information about our worker nodes, how many replicas, the configurations for them, and so forth. So again, we're defining our cluster that's going to be created and provisioned out to these machines. Next slide. So Tim mentioned the Cluster API and how it's an abstraction for really defining a cluster on nodes in Kubernetes. And that sounds very simple on the surface, but the way the abstraction is designed and the way Kubernetes works, this is insanely powerful. The cluster resource at the top there effectively points to 2 different types of resources. How is our control plane going to be configured, and what is our infrastructure going to look like? Next slide. This slide is going to map those 2 concepts, so the bottom 2 abstractions, to the actual implementations we're going to use for our particular build. RKE2 control plane, because we want to have an RKE2 cluster down there. And for our infrastructure, we're going to use Metal3 clusters. And this is the provider stuff that Tim just mentioned a couple minutes ago. As you can imagine, there are a variety of different things you can slot into here. But in this case, given the scope of this demo, we're going to be deploying RKE2 onto a metal cube or a bare metal cluster. Next slide. Like I said earlier, this resource model is reasonably complicated. So I try to trim out as much as possible and give you the high level concepts here. For this step, ignore the metal cubed cluster part. We are just defining the workload cluster itself. And again, in one of the more heinous dumbing down of things, RKE2 configuration sounds like a simple item, but at the end of the day, this is incredibly powerful, getting you what you need from your cluster. So those are the resources I want to care about right now. If you can go to the next slide. For the worker nodes themselves uses a slightly different resource model, but conceptually it's very, very similar. We have the RKE2 configuration, but specifically for the workload nodes and for the worker nodes, and then the machine deployment. In other words, how many of these worker nodes do we want? Where do we want to pull the nodes from? And so on and so forth. And again, we'll ignore the Metal3 specific pieces at this point because we're just talking the cluster API. We're just talking a actual cluster definition, and the wiring it up to the Metal3 pieces underneath is going to happen in the next step. So Tim, could you jump to the cluster video? This next one's going to be fairly simple in the sense that it's all resources inside of Kubernetes. So we don't have to do any fun time skips because it's not actually touching the Metal3 resources yet. And again, for my earlier concept, could you pause it real quick? This is going to enable us to choose when we want to define these. I didn't have to do the bare metal hosts first. I could have done the cluster first. They could have been done at the same time, but for the ease of understanding, our bare metal hosts are inventoried and just kind of sitting there waiting for us to do something. On the left, you can see the output, and I obviously don't expect anyone to read that, but just keep in mind that this is our cluster at the top, and that it comes out of the Cluster API, and then our RKE2 control plane and all of the configuration for that. Hit play, please. At the top right, we're going to see a tail on the CAPI namespace. Again, CAPI is this Kubernetes CNCF project for defining an API and how to provision clusters. What I don't have on here is a tail of the Metal3 pieces. You're just going to have to trust me that actually nothing is happening at this point because we haven't wired those pieces up yet together. So going on the left, can you show me where we are in the video, Tim? Okay. You can see on the left here, somewhere in the middle, scaling up control plane to one replicas, actual is 0. And then what I do here is I show you that output again for the RKE2 control plane. In other words, Kubernetes has gotten our resource. It has said, hey, you want me to create this cluster, but I'm stuck right now. I don't have the actual infrastructure that I can scale it up to, but that's okay. I'm going to keep trying, and I'm going to wait for you to finish wiring up the resources. Back to the slides, please. So our last step, and to sound very cliche about it, next slide, this is kind of where the magic happens. So to quickly reiterate, we have bare metal hosts inventoried in the system. We're able to contact them. We've already proven with the IP agent for discovery that we can get an image out there and tell the machine to boot and do things. So that's really cool. We've defined our cluster. We said, hey, this is RKE2 and all of its goodness. This is what we want to exist on the workload. The workload cluster. Now we want to wire them up. Now we actually have to use the Metal3 pieces that say these bare metal hosts are going to be provisioned in this fashion, and then they're going to get wired into this cluster. So next slide, please. So we will choose the nodes. Tim mentioned earlier that there are multiple options for how and where you want to deploy this cluster to. Obviously, we're just not going to randomly pick a bare metal host. You have decent amount of control on that depending on your needs and what hardware you have in place. We're going to specify the image we want to provision on those, and then the network configuration, which is obviously very crucial, and I can say personally also one of the bigger headaches you're going to bump into, at least at my skill level when it comes to networking. Hopefully y'all are a little bit better off than I am. Next slide. These next two slides, we're going to see mirrors of the previous slides. So while we had previously defined the cluster and the actual control plane for it, now we're talking about all of the hardware pieces. So what is the Metal3 cluster itself going to look like? This cloud designation, I debated whether or not to add this, but at the end of the day, this is a Cluster API flag that says, is this running on a public cloud or not? And in this case, obviously it's not because it's bare metal. And the machine templates have images and a variety of other things that are all around provisioning and building the system itself, not necessarily the pieces to install RKE2 on it. That's going to come later. Next slide. And again, we see this for the worker nodes as well, where we are pushing out that configuration for what these worker nodes are going to look like, getting them all provisioned and wired up. Tim, will you jump to my last video, the one that begins with Metal3? So a lot's going to happen in this next demo. If you pause real quick, top right, we are now tailing the CAP M3. Cluster API or CAPI, the Metal3 implementation of this is in this namespace CAP M3 system. That's what we're watching on the top right. In other words, this is just going to say Metal Cube sees some of its resources have been edited and it needs to do something, so it's going to jump in and start working. Now on the left, rather than show you all of the YAML, I just did a quick grep to show you that there are a number of different resources getting created in here, all related to Metal Cubed. And data template versus machine template is deeper than I want to go for this talk. Just understand that this is going to carry all of the information needed to provision those machines, get them wired up into a workload cluster. Hit play, please. On the bottom right, cluster.ctl is a cluster API command line. It is going to show us the state of our cluster. Obviously, right now, this is going to show us some warnings in the fact that it is not ready. It's still stuck in that scaling up state, which absolutely makes sense. We created our cluster, but we never actually told Metal Cubed, hey, here's the machines I want you to use for it, and here's how you should go about provisioning it. Now we've created those extra resources, you could see that cluster.ctl output start to really flesh out. And I set up a watch on it just so it keeps kind of refreshing for us. All of the different pieces going on, our cluster infrastructure, the control plane, all of the data related to the worker nodes available through this cluster.ctl output. And again, we're looking at it in process right now. So even though this is a recorded demo that I know works, it is very unnerving to see false and warning on screen, but I promise you it's supposed to be there. We rewind 10 seconds for me. I edited that. I knew this was going to happen when I edited that video. I cut it a tiny bit too short there. Hit play, but get ready to pause quickly. And what I wanted to show you is the output from Ironic itself. And wait for it. Pause when you see that table come up. I also have installed in these nodes for debugging purposes the Ironic CLI, so I can get into Ironic directly and ask it questions. And you can see that the provisioning state, the second column from the right, is working on the cleaning state. It's actually starting to get the control plane node ready for it. So hit play, please. Okay, there's all stuff under the covers. You wouldn't need to look at this normally. These are some debugging tools. They help in a demo that you can see that, yeah, these are all the moving pieces and this is everyone kicking into action. Again, time passes where all of this provisioning has taken place and ta-da, everything comes back as the cluster has been successfully created. All I do here is remove the watch so you can actually see it in color, because after seeing a lot of yellow on my screen, it feels very, very good to see a nice bright green ready message on there. So our entire cluster has finished provisioning. If we ask Kubernetes about the resources themselves, you can see the cluster resource now shows as provisioned, basically telling us it's ready to go. If we look at our bare metal hosts from here, you can see that those have been provisioned as well. And then the last of the metal cubed resources also come back as provisioned. So a lot of depth in there and breaking apart those pieces. But at the end of the day, what this entire demo boils down to is I've crafted these resources based on my needs. And you can actually jump back to the slides when you get a second, Tim. So I've crafted the resources to what I need. And go to the last one. We've got our cluster definition. We've configured RK2 the way we want it. We have told our management cluster, here is where our bare metal machines are. Go forth and look around and understand what's on them. And then we effectively wired the two up. We said, now I want you to take this cluster and deploy it on those bare metal machines. Some time later, a little bit of hand waving, and the cluster comes back as ready to go. Last slide. Tim, actually, not to put you on the spot, but do you want to wrap up with the finishing comments?
Well, yes. And I was thinking to like what your presentation or the demo made me wonder is, can you elaborate a little bit on like how the matching of the information we put into the machine templates and the actual hardware inventory works? Because in a practical scenario, I can imagine that I will have a relatively large pool of hardware available, and I will have some view of how that pool is structured, like either by location or by hardware type. And maybe I want to compose my clusters of, I have a particular machine type that I want to be using for control plane nodes, and another type of machine that I want to be using for worker nodes. because they may have accelerators in them that only are useful for the workload, but the control plane doesn't care about them, all that kind of stuff. Can you tell us a little bit about how that works in this context?
Sure. I'd like to point out, Tim, though, that the benefits of a pre-recorded talk like this is that I don't have to field live Q&A. So I'd like to thank you for destroying that for me and putting me on the spot here. That said, I actually kind of figured this was going to be probably the number one question being asked, so I don't hate this too much. If you've ever used the built-in Kubernetes constructs on node selectors for giving hints to where you want your workloads to run. For instance, I have a couple machines in my cluster that are very, very GPU heavy. I'm going to put ML intensive loads on those. You have ways of triggering Kubernetes, these kind of flags on the nodes that say, hey, this is an indication of the hardware profile, and then flags on your pods and your deployments that say, hey, this is the kind of hardware profile I want you to match. Very, very similar here, where in the bare metal resources themselves, we can use these node selectors and say, hey, I want to describe this node, provide some extra metadata that says, I forget the term you used before, but I really liked it, but this is hardware that I have allocated specifically for this. Different network configuration, or we have different hardware running on there and so on. So I will flag those, and then when I go to actually create the metal cubed cluster, if you think back to the start of the third video when I did the grep on all the different kinds and all those different templates, in there we indicate, hey, follow these clues, and I want you to use the hosts that have been tagged with the specific node selector on it, and that's the ones that it's going to pick out of the pool and attempt to apply it to.
Right, and that's also, we also see that on the slide here, right? Under the Metal3 machine template, you have the host selectors that basically point to information that is in the bare metal host, so that like the pair that is meant to go together can find each other.
That's exactly right. Even though this was a completely unexpected question and putting me on the spot, I did know it was coming, so it is sitting there right in the slides for us.
Right. All right. So yeah. So I mean, this is basically all we have for you today. What we've shown you is how we can basically remote bootstrap unprovisioned machines and turn them into nodes in a Kubernetes cluster and basically create a Kubernetes cluster on top of them, all by basically creating Kubernetes custom resources on a management cluster. And even though we've not demonstrated that part, it is relatively easy to imagine that this goes very well with a GitOps operational paradigm where these resources, where the source of truth for these resources is in a Git repository, and the GitOps engine pushes them down to a management cluster, and then it's basically the role or the task of the management cluster to turn those resources into actual infrastructure state, as we have seen in the demo. That's basically all we have, right? Thank you very much. That was a super interesting demo, and yeah, that's, I guess, where we can wrap it for today. Thank you very much for listening, and enjoy the rest of the conference.
Thanks, everyone.